Hi guys, welcome back. And we were discussing in the past video that what is a statistical test. The question is that in the last video and last tutorial we understood that a statistical test is nothing but a partitioning of the sample space, right? A partitioning of the whole sample space of the data. That if the data lies in this position, it's rejection. If the data lies in another position, it's non-rejection of the null hypothesis. The question is that how do we decide what is the best partition of the whole data set? So observe that let's say we decide this test that reject. So therefore, the first what comes up is that we have a model. Then we have the null hypothesis and the alternate hypothesis. And then we have the test criteria. Phi. The goal is that, so this is telling that it's equal to 1 if x belongs to the rejection region and 0 if x does not belong to the rejection region. This is very simple, simplistic. So an example that we have seen is that let's say x1 x2 follows Bernoulli p, and h1 is p is equal to half and p is greater than half. So and test criteria we have seen that x1 plus x2 is equal to 2. That's the test criterion that of rejection. So you can see that it's equal to 1. Phi is equal to 1 if x1 x2 greater than 2 is 0 if x1 plus x2 is less than 2. Right? That's a test criteria. You can think about that. Think about it in this way. Understand the data is of two elements, consists of two elements here. In general, literally phi of x. So the goal is that to understand that what is the best partition, what is the best test. So when you divide this whole data set, it can happen. So when we keep on tossing and there are various different samples, right? Various different ways, it can happen that. So if you say if you take p is equal to half, and if you take p greater than half, you don't know the value, but p is let's say greater than half. In both cases, when you toss, in the real life scenario, you keep on tossing in both the cases. In some cases, when p is equal to half, let's say you don't know in other cases when p is greater than half, let's say p is equal to actually in p is equal to 3 by 4. In that case, that means it's p greater than half. It can so this two data set can be 0 0 1 1 0 1 and 1 0, right? Here also it can be 0 0 1 1 0 1 and 1 0. So we have seen that we have rejected if this is this. But even if p is equal to half, there is some probability of this happening, the rejection of, so this is the null hypothesis, right? So even if p is equal to half, there is some probability. This is probability 0.25 of the truth. It actually has happened that p is equal to half. That is null hypothesis is true. But since it is given 1 comma 1, that's why it's rejected. So therefore, it can happen that due to some probabilistic chance that even if Even if the null hypothesis is true, it has been rejected, or vice versa, right? So understand the scenario. For p is equal to half, there can be a case like out of 100 times, out of 100 such samples, 25 such samples will give half 1 comma 1. That is, in 25 such samples it will be rejected if it's such two pairs are sampled 100 times. 25 such pairs will reject it. So therefore the idea is that this test is not actually always be true, this reaction. There'll be some errors to it. What are the errors? That is why where it comes this table, that true versus um, test. What the test has decided. The test is a very strict case, right? The test is a very strict policy that the two cases when actually H naught is true, H naught is not rejected. So we can write this as in this way, that the truth that H naught is actually true and H naught is false. That is H1 true. In this case, the H truth is that H naught is true. That means P is equal to half. In that case, there are certain cases where, like I have seen, it's shown you in this case, there are certain cases where the test rejects it. That is, H naught is rejected and H naught is not rejected. You can say, or H1 is accepted. So in this case, observe that if H naught is false and H1 is rejected, that's a good thing. That is what we want. If H naught is true and H naught is not rejected, rather H1 is rejected, that's a good thing. Or H1 is accepted, that's a good thing. That is what we want. So truth and the decision, when they're matching, that's good. But there are other two cases. Like you can write this as this. But there are other two cases where H1 is true, but it is rejected. Another case is that where H naught is false, H naught is true, it's rejected. Another case is that when H naught is false, it's accepted. So both are errors. These are errors. This is called type 1 error, and this is called type 2 error. So you can see by experiments, and this you cannot reduce both of them together. Why? You cannot reduce both of them together. So the one way to reduce type 1 error is to always the one way to reduce type 1 error is, you can always reduce type 1 error to the minimum. Okay. That when h naught is true, then like what will happen? You can always reduce type 1 error to a certain extent. Okay, let's say we always accept h naught. We always accept h naught, right? Then there will be, if you always accept h naught, then what will happen? Like for all data point, there is only one part. So we always accept h naught. Then what will happen? Think about it. If you always accept h naught, what will happen? Think about it and let us know in the comments below. What will happen? What will the table look like if you always accept h naught? That means it's never rejected. Okay. That means it will never be rejected. So this one is 0. This probability will be 0. Type 1 error will be 0. That h naught is true, but h naught is rejected. That will never happen because h naught is always accepted. That's the test criteria. That the partition is that phi 1 is equal to R region is null is equal to phi. So in that case, h naught is 0. The type 1 error is 0. So type 1 error is 0. Type 1 error is what? In case of always accepting h naught, type 1 error is 0 because when h1 and h naught is true, I mean h naught is never rejected, so type 1 is always 0, right? But type 2 error will be maximum, will be like really huge. Also, when you want to reduce type 2 error, that means always reject h naught. Type 1 error will be max, like more. So therefore, both type 1 error and type 2 error together cannot be reduced. Cannot be reduced together. So what is the formal definition of type 1 error, type 2 error? Type 1 error is nothing but probability of rejection given rejection of h naught given h naught is true. And type 2 error is that probability of acceptance of h naught given h1 is true. That means h1 is true means that h naught is not true. So we are accepting h naught given that it's not true. Okay, is this scenario. So if we carry out this probability, if we find this probability, now how do we find this probability? That's the question. So let's say the test is h naught is p is equal to half versus h1 is p is equal to 3/4. If we see these two tests, you will see that type 1 error and the rejection region R is nothing but rejection of h naught. Means rejection of h naught is equivalent to what? Rejection of h naught is nothing but up space, right? It means that x belongs to a certain region R. That means reaction of h. That means equal to, that is the time when phi of x is equal to 1. That means it's saying that the one case where if x is equal to R, 0 if x not equal to R. That means rejection if x is equal to R. So therefore, we are rejecting H1 is equivalent to a case that this data point belong to specific rejection region R. So therefore, this type 1 error, T1 error is equal to probability that X curl belongs to R given H0 is true. Here in this case, H0 is true is what? P is equal to half, and X belongs to R means X1 plus X2 is equal to 2. That was the reaction region, right? And the previous video. So if you check the reaction region, that was the, also we have discussed it here. One example was this. And type 2 is nothing but probability X curl belongs to R given, that is, does not belong to R. That means acceptance of H0 does not belong to R. That means it's 0. That means X1 plus X2 is less than 2 if given H1 is true. That means, let's say, P is equal to 3 by 4 in this case. So we calculate these two things, and this will come out in terms of, in terms of numbers. Certain numbers. The question is that we can find out this. So we're going to reduce type 1 and type 2 error, both, but we cannot reduce both together. So what we do is that we fix the type 1 error. The type 1 error can at most be this. Can at most be this, less than, like, can at most be, let's say, we fix the, this is called the level of significance. It's 0.05 or 5% error. And now given this 5% error, we fix this alpha. We fix that probability, we fix that this can be at most alpha. Now, given that the type 1 error can be at most alpha, we can reduce the type 2 error, right? So therefore, the best test is the test with the minimum type 2 error given that type 1 error is at most alpha. This is the basic idea. Now we can question that why didn't we do the other way around? Why didn't we fix the type 2 error and reduce the type 1 error? There are many dimensions to it, many philosophical dimensions to it. But the idea is that we want to reduce, we want to make sure that we reduce the maximum amount of, when H0 is false, but it's actually accepted. That's a bad thing, right? If in this case the person was guilty, is not guilty. If the person is guilty, that in the see the example, if H0 is person is not guilty, so H1 is false means person is guilty. What? We are accepting that person is not guilty. That is the amount of probability we want to reduce, right? We want to reduce that probability of that given the person is guilty, we should minimize that the person, minimize the probability of not proving the person guilty. So therefore, there are some philosophical dimensions to it. The idea is this, that therefore the go understand that this is what people have decided. Now it's logical. We will make another video out of it. Why it is that. But the goal is that given we will fix type 1 error think in algorithmic way, that we will fix the type 1 error to a certain degree and then minimize the type 2 error, because we cannot minimize both. And this is called, so 1 minus type 2 error is called the power of a test. So therefore also understand that the power of a test, so if we fix type 1 error, the type 1 error is just based on h naught. It's nothing not based on h naught, right? So we have drawn four options for such rejection region. Now, how to understand which is best? The data which not only are the rejection region, which not only so when will we reject h naught? We reject h naught. We can reject h naught even at 1 or 2. Or when we increase the data, we can reject h naught at any point greater than, you know, n by 2. The goal is that the rejection region should not only anti-support h naught, not only it anti-supports h naught, but it should also support h1. If it just anti-supports h1, h naught, then both x1 plus x2 is equal to 2 and x1 plus x2 is equal to 2 both are good test. Understand this. If it anti-support h naught, it does not support h1, both x1 plus x is equal to 2 and x1 plus x is equal to 0, both are good tests. But x1 plus x is equal to 2 also supports h1 because p is greater than half. But this does not support h1. So therefore, this is a better test. How to incorporate this into the whole picture? By minimizing the type 2 error, but not the type 1 error, because type 1 error is only about h naught, nothing about h1. Type 2 errors is where h1 is coming into the play. And that's why it becoming better test. Right? Now you know the reason why type 1 error is type 2 error reduced. Not type 1 error is reduced. This is the basic idea. So therefore, how do we get the best test? We find that R for which type 1 error is at most greater than equal to less than equal to half. And then fixing that, we find the test with minimum type 2 error. Or also 1 minus type 2 error is called power. So therefore minimizing type 2 error is nothing but maximizing the power of a test. Simple. So therefore, this is the step. We have first a model. Then we have the hypothesis. And from the hypothesis, we have the rejection region. For the rejection region, we find the type 1, fix the type 1 error is equal to alpha. And then we minimize type 2 error. And we get or make the best, most powerful test. And that's where the best test comes up. And we will see that Neyman-Pearson lemma gives a way to solve that. Does always a best test exist? No. So we will discuss in the next class that will be happening in our course, Statistics FC course. I hope it gives an intuition idea about why we care about the most powerful test and how we care about it. All the best, guys, and I will see you in the next video. Stay tuned and stay blessed. So there are two parts of the video. One is understanding what is statistical test. Next is finding the best test. So those two tests together makes the whole dimension of the best test that we need to know. Thank you, guys, and I will see you in the next video. Stay tuned and stay blessed. Bye-bye. Have a great day ahead.